Unit 2, the molecules of cells. Objectives. How is an atom organized? What kinds of bonds join atoms together to form molecules? What are the types of chemical reactions that are important for living things? What are acids and bases, and what does pH have to do with them? What are the important inorganic and organic molecules that organisms must have to live? Looking back at figure 1.2 from chapter 1, you can see how we're going to start. Looking back at figure 1.2 from chapter 1, we'll see how we're going to start very small at the atomic level. We're even going to get into some subatomic particles today too, and go up to the molecule level before we get into actual living things with cells and so on in later units. Chemistry is the science that explores the structure, composition, and changes of matter. So, what is matter? Matter is anything that takes up space and has mass. We have 4 different states of matter: solids, liquids, gases, and plasma. So, as we can see, with solids, if we add energy, can liquefy things, add more energy, things can become gas, and even more energy to the plasma level. So more on matter. There's some generalizations for each different type. If something is a solid, molecules that make up a solid are arranged in regular repeating patterns, held firmly in place but can vibrate within a limited area. If something is liquid, then these molecules flow more easily around one another, and they're kept from flying apart by attractive forces between them. We'll see hydrogen bonding in water as an example of this. And liquids are going to assume the shape of their containers. With gases, we can see that the molecules are more diffuse, and they fly in all directions at greater speeds. And they're so far apart that the attractive forces between them are insignificant. With plasma, again, this is increasing energy. At very high temperature of stars, this is an example, where atoms lose their electrons. The mixture of electrons and nuclei that results is the plasma state of matter. There's different kinds of matter. A mixture is a combination of 2 or more substances not chemically bonded together and keep their separate identities and purposes. Hamburger, sugar water, blood, sweat, tears. Different kind of matter is being a compound. This is 2 or more different elements which are chemically bonded together. H2O, NaCl, HCl, C6H12O6, that's being water, sodium chloride, hydrochloric acid, and glucose, respectively. Looking at matter as well, all matter, living or non-living, is made up of elements. So an element is a substance that cannot be broken down into simpler substances by ordinary chemical means. And what we're talking about by ordinary chemical means is pyrolysis, application of heat, electrolysis, application of electricity, and photolysis, application of electromagnetic radiation. So, looking at the 92 naturally occurring elements, they serve as building blocks of all matter. And if you look at the periodic table, there's more than 92 elements. And so these other ones are human-made, and we're not going to focus on them as much in a biology class. So here are 6 elements to memorize. And these make up 95% of organisms by weight. So like I say, even though there's 92 that we'll be looking at that are biologically more significant, these 6 we're going to focus on more. So carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. So our acronym, or you can make up your own, is CHNOPS. So if an element is a unit of matter, the smallest unit of an element is an atom. And that's going to be the smallest discrete unit of that element that displays the characteristics of that element. It can exist either alone or in combination with other atoms. So if we're looking at atoms as these tiny building blocks of matter and of elements, they're really tiny. If there are 7.5 billion people on Earth, and this is estimate as of May 2017, and we can see how many zeros that includes. If we're looking at that compared to a little BB from a BB gun, that has 3 quintillion atoms in it. So a little perspective here from our 7.5 billion people on Earth. If you're taking one of these tiny little BBs, 3 quintillion, that's 21 zeros. You can go ahead and count them. So atoms are really tiny. If we're looking at what atoms themselves are made of, there are 2 major parts to an atom. There's a positive center or nucleus, and within that nucleus we find protons and neutrons. Protons have a positive charge. Neutrons are neutral or uncharged. The second part of an atom is this negative zone or electron cloud, electron shell, or energy level. There's several different names that they refer to this other zone that is around the nucleus. The only subatomic particle that we're concerned about in this negative zone are electrons, which are negatively charged. And so, as we'll see, these electron shells or orbitals, in the first one it can contain up to 2 electrons. Each one after that wants to have 8 electrons. This is the octet rule, and we'll look at this a little bit more momentarily. So if we're looking at protons, neutrons, and electrons, they are subatomic particles because they're below the atomic level. So if we're looking at a representation of a helium, if we look at a representation of the helium atom, this central location represents the nucleus, and so we see we have 2 protons and 2 neutrons represented here. And so that's going to have an overall positive charge because of the protons. Electron orbitals will be represented several different ways. You'll commonly see them represented much like an orbital you would see of like planets, or in this kind of scatter plot representing the likelihood of where you're going to find an electron. So to get some perspective, with models and drawings like these, it shows that the electrons appear to be somewhat close and even kind of tidy, as though you have this expected trajectory of the electron, and that's not quite how it is in real life. In fact, in actuality, an atom is mostly empty space, and the electron does not orbit in neat circles. To get some perspective, if we used a stadium to represent an atom, the nucleus would be about the size of a pea in the center here, and little tiny specks of electrons would be zooming about the stands here. And they may not even stay in the stands. They may sometimes wander out of the stadium from time to time. Some important terms that are used a lot in chemistry. First, if we're looking at a neutral atom, this has an equal number of protons and electrons. As we just looked at, protons have a positive charge and electrons have a negative charge. So if you have a balance between that, the atom is neutral and has no net charge. Looking at atomic number, this is going to be the number of protons in the nucleus. And shown here, whenever you see 2 different numbers next to an atomic symbol, this represents carbon, the smaller of the 2 is going to be the atomic number. And that's always going to equal the number of protons. If you change the number of protons, you have a different element. The atomic mass, or the atomic weight, is equal to the number of protons plus the number of neutrons. And In our book, it's going to be rounded up to a whole number. If you look at other periodic tables or information, you may see, excuse me, the mass number or atomic weight is the number of protons and neutrons that an atom has. Sometimes you'll see this as a whole number that has been rounded up or as a decimal. This is because protons and neutrons contribute about 1 mass unit, and electrons are nearly weightless. So from this, along with the atomic number, you can determine the number of neutrons present. So you subtract the atomic number from the mass number to get the number of neutrons, right? So if this is neutrons plus protons, subtract protons, you get neutrons. Whenever we have an electrically neutral atom, the positive charges of protons in the nucleus are bounced by the negative charges of electrons. Electrons, as we said, move about the nucleus in orbitals or shells or energy levels. And the first two can contain up to 2 electrons. Everyone after that holds 8 electrons. So this is the octet rule. Valence electrons are those that are in the outermost shell or orbital. This is going to influence bonding or reactivity, as we're going to see. So for hydrogen, if we have our atomic mass and atomic number, so if we subtract that, right, 1 minus 1 is 0, so there's 0 neutrons. There's just 1 proton represented in this nucleus. And if it is uncharged, and so we're going to have an equal number of positive and negative charges, we have 1 electron. So this is about as simple as you can get with hydrogen. So notice that we have 1 electron in this first shell or energy orbital. With carbon, atomic number 6 and mass number 12, so there's going to be 6 protons and 6 neutrons represented in this nucleus. If it's also electrically neutral, there are 6 electrons. So to place those in the correct orbitals, we have 2 electrons represented by these blue balls here in the first orbital, and then we can hold up to 8 in this second one, but we only have 4 left, so that is why we have a total 1, 2, 3, 4, 5, 6 electrons in carbon. So with nitrogen, you can see that if we have 7 protons, right, the atomic number, and if we're fitting in 7 electrons, you have 2 in the first orbital, 5 in the second, and so on. With oxygen, if we have 8, 2 in the first, 6 in the second, and so on. So with phosphorus, we're starting to get a little more complicated. If we have 15 protons balanced out by 15 electrons, 2, 8, so that's a total of 10 for those first 2. We have 5 left over for the third orbital. So sulfur, 16, and so 2, 8, and 6 electrons. So you can compare how electron shells or orbitals vary depending on how many electrons are present.